talking about today? Where are my notes? I have notes. So let's take a couple minutes to get people in here, I guess. And I made a few changes to my computer setup here, so if like the audio's off or if something's off, can you please let me know, and I can or if it's okay, can you also let me know that too, so that way I can fix stuff if I need to. But I was just looking through because I need to find. I made some notes last week, but I can't find where they are. Give me a sec. So I don't actually have the notes with me, but I guess we'll just have to do it live then. I do have the textbook, so I guess I can go through that along with whatever we covered last week to get an idea of what I want to talk about. What's this? Oh, okay. Thanks, dude. What did we do? Wave equation. Vector. Subpointing vector. Why don't we do this? Why don't we? What was the last topic that was covered in lecture? Can somebody please let me know? This week? What did they cover in lecture? I wonder if my sound's even going through. Is my sound going through? Can somebody confirm? I see 8 people watching, but I don't see any. Nobody's commented. I can't tell if you can hear or not. So it would be extremely useful if you let me know if we could confirm, do a sound check. Like that should be moved probably. Can we? It's not locked, is it? It's not locked. There we go. That's better. This is tutorial 3. And I'm kind of confused because I don't see anybody saying anything. Or I wonder maybe if my thing is just glitching. Maybe people are saying stuff and I can't tell. Because that wouldn't be the first time. Oh, people did say stuff. But I don't see it. That's so weird. Okay. Okay. Sorry. So apparently people are saying stuff, but I couldn't see it for whatever reason. Okay. Hopefully that doesn't happen again. So you talked about standing wave ratio and input impedance. Okay, so if you talked about standing wave ratio and input impedance, then you means you guys talked about reflection of plane waves, and you talked about transmission, that you skip oblique incidence, and then you go... Okay. So here's what we're going to do. We're going to first move the mic over a little bit, so sorry if this makes a bit of noise. Okay. Now what we're going to do is we're going to talk about reflection. We're going to talk about reflection in plane waves. So let's talk about reflection. I really wish I had my notes here that I made last time. They were fairly useful, but my entire setup's like a bit of a mess. Hold on, are these the notes? Actually, no, those aren't the notes. Okay. Anyhow, let's just do it off of what we remember. So let's talk about reflection then. So the idea of reflection is this: if you have waves, and you have waves that well, let's talk about the reflection coefficient first. So let's talk about the reflection coefficient. So the reflection coefficient gamma is defined as eta 2 minus eta 1 divided by eta 2 plus eta 1. And this is considering a situation kind of like this, where let's say you have some boundary. They usually put this at z equals 0. You have two regions of space, 1 and 2. And that means this, let's say, has mu1, epsilon 1, and therefore has eta 1. And this is mu2, epsilon 2, and therefore eta 2. And what that means is that, well, that doesn't mean anything to you right now, but basically what you have is you have some electric field, and this is usually defined as EI, as the incident field. That sign's drawn too close. EI as the incident field. Then you have some of that field, this is a boundary of course, and you imagine that these two regions are semi-infinite, meaning this is half of infinity and this is the other half of infinity. So this is negative infinity, this is positive infinity, and this region goes on forever. So the idea is that we have also a transmitted wave, and then you'll have some partial reflection here, right? And so maybe we can do this in a different color so it makes a little more sense. So the idea then is some of this wave will be transmitted, some of it will be reflected, and so this is the kind of situation that you have at any given interface. In the general case, an incident wave will be reflected and partially transmitted. So you can imagine when you look at, let's say you look at a window, and sometimes when you look at the window, you can kind of see, well, you can definitely see through it if it's a good window. And in some cases, you might be able to see reflections of like yourself in a window, and so that's what you're seeing is the light being reflected off of the window and being reflected back at you, and therefore you can observe it to see what it actually is. So I guess that's the most practical way of thinking about it. Another way to think about it is if you have glasses, for example, some people have polarized glasses, like reading glasses, and so the light goes through even if you don't think about polarized glasses, think about, or like don't think about reading glasses, but think about any pair of sunglasses, and sunglasses reflect majority of the light. That's what the purpose of them is, and they will transmit some of the light. So you can imagine that electric field, some of it's reflected, some of it's transmitted. Now we want to be able to quantify this behavior, and we want to be able to understand how this behavior varies in different cases. And so what we do is we define these things called like the reflection coefficient, the transmission coefficient, and all these kind of things. And they basically let us relate certain field parameters in one region to the other to be able to better predict how the fields will behave. So in the general case, you can say that the reflection coefficient is dependent on the material spaces. So if this is air and this is, I don't know, some dielectric, the properties will depend on the material space itself. But another way to think about this is the reflection coefficient is defined as the magnitude, let's call this the magnitude of the reflected wave divided by the magnitude of the incident wave. Okay. Similarly, we can define something called the transmission coefficient, and this, like the reflection coefficient, will tell us how much of the incident wave is transmitted through the medium. So we can call this the transmission coefficient, and the transmission coefficient, we call it tau, and the transmission coefficient is defined as, it's actually 2, so that looks kind of awkward because so it's 2 eta 2 divided by eta 1 plus eta 2, and as you may expect, this similar type of thing can be written, but in this case it'll be the magnitude of the transmitted wave. So this will be ET phoning home, no, it'll be ET magnitude divided by the incident. So how much of the transmitted gets through with respect to how much incident went through, or incident was subjected to the entire system. Just want to refresh my chat thing here on this side to make sure I didn't miss anything, because apparently I was missing stuff. Okay. Yeah, so if you ask questions and stuff, if you're asking questions, or if you're saying something and I don't respond, it's not because I'm ignoring you. It's because my feed might not be getting refreshed. So if that happens, send me like a direct message through the Facebook Messenger, and that way I'll be able to figure out if I'm missing messages or not. So because I don't know, it's acting kind of strange. Well, it was, at least. I don't know what to do now. So you have these two things called the reflection coefficient and the transmission coefficient, and of course they will be related to each other somehow, since the reflected field and the incident fields are related to each other somehow. And so what we can do is we can say that the magnitude of the incident should be equal to the magnitude of the reflected plus the magnitude of the transmitted, because energy has to be conserved, so the magnitude of whatever electric field came in has to be equal to the reflected plus this. And then what you can do is you can divide this whole thing by E. Well, actually, do I want to do it that way? No. Do I want to do it that way? Do I want to do it that way? Because if I divide both, sure, let's do it this way then. So let's just divide everything by the magnitude of EI. And this is an important property. So you divide both sides of the equation by EI. And the result of this is that 1 is equal to gamma plus tau. So that means the reflection coefficient plus the transmission coefficient have to equal 1. This is an important property. And so we can write here, I guess, properties. So let's write here properties and not just make that kind of float around. So these are properties. So this is one of the properties. And this helps because if you know one, then you can find out the other using this sort of equation. And again, this is conservation of energy. So this is nothing unique to electromagnetics. This is just physics, the laws of physics. We have the other property is that both gamma and tau are dimensionless. Since they are both ratios of the exact same quantity, they must be dimensionless. My arrows are turning out kind of weird. That one's better. And then we have another property that the magnitude of the reflection coefficient has to be less than, well, between 0 and 1, basically. Because you can never reflect more than you transmitted, or more than you sent in the initial. So the magnitude of the reflected wave cannot be greater than the incident. Either it's all reflected, or part of it goes through. If it's all reflected, the reflection coefficient becomes 1. If nothing is reflected, the reflection coefficient becomes 0, but it must be somewhere between. So you must have either it's reflected or it's not. So those are the two extreme cases. So it has to be magnitude has to be between 0 and 1. I forgot to add something here, that they're dimensionless and may be complex. So in general, you can have a complex reflection coefficients and transmission coefficients. What that means is that along with the magnitude, it'll change the phase of the reflected wave. So the incoming wave might have a certain phase, and then the one that gets reflected might have a different phase, and as a result, you would have a complex quantity, because that's really what complex quantities mean. There's a magnitude component and a phase component to it. How do you know what it's going to be? It'll be depending on the medium itself, and it'll probably be very explicitly stated in any questions that you have or have to deal with. So that's the reflection coefficient and the what? And the transmission coefficient. There we go. One thing I want to make note of, I should write this in red so that everybody pays attention. Or I should say let's just say gamma and tau are defined in terms of E. Well, E, not H. This is important. And you might think, yeah, it's pretty obvious because you just literally used E in both the cases. You used E here. But what might happen in a question is, and they try to trick you sometimes, they give you H in both cases, and it's very tempting to go through and try to do this with H. Because they'd be like, oh, it's just H transmitted divided by H incident. And it's not. The magnitudes might be the same, but there's a sign difference. I can't remember what the difference is, but there's some sort of sign changes, and I don't remember what it is. And I don't remember what the general case is for the magnetic field, so I would recommend always use electric field when you're doing all these type of things. Don't use the magnetic field. It's just extra stuff for you to remember and take care of. Keep in mind. Yeah, this is not an R, guys. This is a gamma. So there's gamma, there's the capital gamma that looks like this, and then there's the lowercase gamma that looks like this. So, yeah. It's not an R. Okay. Let's talk about the standing wave ratio, because I think that's all we have left before we can say that we're done this thing. He wrote 1 plus gamma equals tau. Did I write that wrong? Sorry, it is 1 plus gamma. Sorry. 1 plus gamma. It's 1 plus gamma. That doesn't make any sense. Why would it be 1 plus gamma? The reflected plus the incident equals that. Wait, what? Or is that just a manipulation of the other things? Oh, no. It's because it's the, it's from the boundary conditions. That's my mistake, sorry. It shouldn't be, ignore this. This is not relevant here. This is what happens when you do things off the top of your head. That's not right. It's this. Just leave it like this. That's it. That's the property. Sorry about that. That's my mistake. Thanks for pointing that out. I wonder why that is. Anyhow, so if you think about the standing wave ratio, let's talk about the standing wave ratio, because this is useful for a couple of topics, the idea of the standing wave ratio. Why is that the case? It's a manipulation of, so what I'm doing is I'm looking at chapter 10.8, or section 10.8. If you look at the equations from 10.8, you can manipulate them, and that's the result you get. So physically speaking, I was thinking about it a different way, but if you break it down according to the, like, so if you take a look at 10.7, 10.8. Yeah, no, take a look at section 10.8, and they break it down step by step there. And rather than going through all that stuff, I guess you can take a look at that. So if you're still having trouble with it after you see that, then let me know, and we can talk about it there. It's because you can basically break up the components in different cases and doing, and then boundary conditions and all that kind of stuff. So it comes from that, not from what I was saying, because I was assuming the energy is constant, but it's not, because it's boundary conditions. Okay. We should probably move this over a bit. So this, in itself, is a, or it can be, I should start using these lines and shit. Probably make things much more neater. Let's do that. I have a mouse, why not use lines? Let's use lines. Let's put like an arrow at the end of it too. Let's be fucking fancy. There you go. Okay. Z equals 0. Okay, so the idea of the standing wave ratio is this. If I have some incident wave and I have some reflected wave, they're going to interact in some way, right? So if a wave's coming in like this and then a wave's going back like that, you remember from physics 125, 120, no, is it 211? I don't know. Standing waves on a string. This is a similar idea to standing waves on a string. It's basically interference between the two waves, right? So you have one going forward and one going backwards, therefore they will interfere in some way, and they will create some patterns. And so the thing that we have to observe here is what's the relationship between these patterns and how can we define the standing wave ratio itself. So the way I think about this usually is, imagine you have some incident wave. So let's draw then the incident wave as the red one. So I'm going to try to make this fairly symmetrical because it makes for simple explanation. So if you have some incident wave that was 4, this is 4, and this is 4. I should probably start on the other side. That's what I should do. That's a mistake. So let's start on this side. So let's go, that's 4, and that's 4, and this is for here, and so on. So this will go on for another sort of cycle thing. Okay, so let's call this EI. Okay, that's your incident field. Now, you will also have, and I'm assuming it reaches 0 at z equals 0. Now you're going to say, how do you know it does that? It doesn't. I don't know that, but I'm assuming my z equals 0 is right where this thing equals 0. You can have it be here if it's defined in terms of a cosine. If it's defined in terms of a sine, then you would have this condition. The difference is literally a quarter wavelength, so it shouldn't make any difference whether you take a sine or a cosine. And you can determine what that is based on, whatever conditions you're given. So then what you might have is, for example, this is an example. This is not general. This is not the thing that happens every time. Like this is not, set in stone that it must be this way. But let's imagine then that our reflected wave does something like this. So let's say it loses some of its magnitude, so it becomes slightly smaller, and let's assume that it is 90 degrees, or it's 180 degrees phase displaced from the incident wave. And if that's the case, then it'll look something like this. And so this is going to be ER. That vector sign at the bottom looks so nice. So happy with that. That's decent too. So then the idea is, what's the relationship between how these things interact? So let's imagine then these are interfering with one another, and if there's interfering with one another, then maybe what we can do is let's extend this down here. Is that what I want to do? Sure. So what you have is basically, let's not even extend it, let's just leave it. Let's just think about this. Let's quantitative, or qualitatively, not quantitative. Qualitative, let's analyze. So now you have certain points of interest here, right? You have points of interest here. This is a point of interest. Why? Because both things are maximums there. You have points of interest here. Why? Because both things are minimums there, or both things are 0 there. You have another point of interest here because, again, this is maximum conditions. I shouldn't say maximum, but I should say these are extreme cases, right? So you have another extreme case here because it goes to 0. You have another extreme case here because they go to maximums. You have another extreme case here, and so on. So you see that there are some points of interest, right? There are regions, or there are points in space where the wave has a certain behavior, right? So you see here that there is a maximum here, minimum for the reflected. You see that here there's a maximum reflected, minimum for the incident, and so on. So these regions of space are actually of interest because they describe how the resulting wave will basically behave, right? Or the standing wave itself, how it'll actually behave. So what the standing wave ratio is, I'm just looking through for if there's anything I may have missed in my example that I have here. And I don't think there is. No, there's not. So what the standing wave is basically, imagine if I had here, imagine if I have at this, we want to do this thing here. Let's have this thing here. This is a point of interest, and this is another point of interest, right? So let's imagine then that here we have this thing E1 max, and here we have this thing E1 minimum, right? So that's the minimum point of the electric field, that's the maximum point of the electric field. And what I'm going to do is I will define this, if you recall from the actual these equations here. From these equations here, we can describe this as being equal to, that looks weird. We can describe this as being equal to, let's call it EI magnitude times 1 plus gamma, and let's call this thing EI magnitude 1 minus gamma, because this is the reflected wave. So 1 minus describes basically in the opposite direction, so the total magnitude of this wave is 1 minus, this one would be 1 plus. I don't know how much of this he covered in lecture, so if you're confused at any point, please let me know, or how in detail he was. So the resulting is this sort of pattern, and so what we do is we define then this sort of standing wave. The result of the standing wave will be basically the, I don't want to say it's the sum, but these two will they'll interact in some way that sort of creates a sum-like behavior, I guess you can say. It's not really a sum. I don't know what to call it. But basically what we have is we have that S, the standing wave ratio, is equal to the magnitude of E1 max divided by the magnitude of E1 min. So it's the maximum divided by the minimum. And again, these aren't physical, like if you were to go into nature, you wouldn't find a standing wave ratio. These are quantities that we're giving to the waves and to the system to be able to better understand what's really going on, right? So the standing wave ratio, reflection coefficient, these are ways of quantifying observed behavior. And so what this becomes is, because these two things will cancel, you'll get this is 1 plus the magnitude of gamma divided by 1 minus the magnitude of gamma. And this equation, so you can look at this type of thing. I should probably add these in all cases wherever I can, but this I should say see section 10.8, because I don't want to spend too much time on this stuff either, because a lot of it's in the textbook and a lot of it's been done, so I don't want to just be here the entire time doing this. But one thing I want to mention here in this case, with these purple dashes that I've drawn, is I want to mention that this, if this is 0, then we call this minus lambda over 4. This is minus 2 lambda over 4. This is minus 3 lambda over 4. This is minus 4 lambda over 4. This is minus 5 lambda over 4. This is minus 6 lambda over 4. And there is some significance to why I'm doing that, right? So when you look at this interference pattern, or you look at this where the maximum and the minimums occur, so because you might get questions where they ask you where the maximum of the magnitude occurs and where the minimum occurs. So we can say that the max magnitude of E1, let's say. So the maximums, let's take a look at this. The maximums are these points, right? So the maximums are these, are where it's non-zero. So where it's non-zero, you have, what are these? These are basically these regions where they're odd, no, they're even they're odd multiples. They're odd multiples of lambda over 4, right? So if they're odd multiples of lambda over 4, then you can generalize, and let's call it Z max takes place at every lambda over 4, basically. Every odd lambda over 4. Let's call it n lambda over 4, not n lambda. Let's call it n plus 1. 2n plus 1, not n plus 1. Lambda over 4. And that is for n equals 0, 1. That's not 0. Let's say 1, 2, 3, and so on. So the first maximum is at when n equals 0, right? So this should be 0, 1. I should start this count from 0. This count should start from 0. 0, 1, 2, and so on. If I start at 0, the first maximum should be negative. So maybe we can erase that, move it all over a little bit. And this is z max. So if this is n is 0, the first maximum is lambda over 4. If n is 1, this is negative 3 over 4. If this is 2, this is negative 5 over 4. So you see these maximums occur. Because you might get asked questions where what's the closest maximum to the interface or to the boundary or whatever. And then in the minimum case, you can imagine it's just the even multiples. I wrote maximum again. So the even multiples, or just, you can say it's 2, 4, 6, or you can say lambda over 2. So why don't we just call it n lambda over 2 for n equals 0, 1, 2, like that. So the first one occurs at n equals 1. So that doesn't, how do I want to do that? Do I want to start the count from 1 and then include n plus 1 divided by 2? Or see, there's a bunch of ways. The thing I'm getting confused, or the thing I'm getting double-minded about here is, depending on which way you count or where you start your n from or your m from, then this equation changes, right? So if I say n equals 0 here, there's a minimum at 0. If I say n equals 1, this is lambda over 2. This is lambda over 2. Yeah, this is fine. We just keep it this way, sure. So these are your minimums. So you can, if you get asked this question, you can, this is the approach that you have to take for a case like this, and how to actually determine these regions. Any questions about this? That's really all the theory I wanted to cover. I don't think there's anything else that needs to be covered. Is there anything else that needs to be covered? I don't see anything else that needs to be covered. Because if there's no questions, then what I'm going to do is I'm going to do the midterm. I think the midterm is this midterm from last year? Midterm 2018? Last year was 2018, right? I think it was. I hope it was. What will we use these values? I'm not sure I understand your question, what you would use these values for. You might not use the values, but you might be interested in knowing where the maximum occurs, where the minimum occurs. In a practical application, that might have some relationship to where you're measuring something or where you're standing. It's very difficult to give you like a real world application because a lot of these concepts are very specialized into what this is. Like it's relative to, like, maybe it's related to some sort of electromagnetics or some. In most cases, you can say this has a lot to do with optics and stuff like that. So these type of interference patterns and stuff would be seen in optics, photonics, and manipulating light in different mediums to be able to do certain things. Because there's some very interesting things you can do with, if you can understand how these relatively simple concepts behave in a bigger region. So in terms of this, what would you do with this? You might be asked to find just where the first minimum is from the boundary. What would you do with the value of the minimum? I don't know. You might be asked to do something with it, but I don't think there's anything. Yes, I do have a copy of the midterm. It was sent to me yesterday or the day before or something like that. So I haven't solved it yet, so we can solve it together. Although it looks very similar to things I have solved before, so I don't imagine it being overly difficult. But you never know. And since we are trying to learn stuff, I will do my best to explain as much as possible why things happen, what's happening, and it might be the case that I might trip up here and there because, you know, shit happens. But hey, what are you gonna do? So let's do this. Question 1. I'm not gonna write the questions out. I'm just gonna write the answers because you should. Does everybody have access to the midterm? I hope everybody has access to the midterm. Let's just write them out so they'll be complete. So let's go A. I'll abbreviate wherever I can. So let's write frequency domain point form of Maxwell's equations. So let's do that. The first one is the curl of ES is equal to minus J omega BS. The second one is, how does he do this? Does it say? It doesn't say what kind of region, so I'm just going to write J plus JS plus J omega ds. And this is all the currents lumped together. And then we have the divergence of ds is equal to rho vs. And then the divergence of bs is equal to 0. So I guess bullshit does not diverge, it only converges. I would argue against that, but what do I know? Part B. Write the time domain point form of Maxwell's equations and include the unit. What? What unit? How does an equation have a unit? An equation that relates multiple variables. Okay, let's try this. In time domain, the curl of ES is equal to point form B over T. And I'm going to think about this unit thing. Oh, I forgot to write the question. Oh no. Let's write the question. Write the time domain point form of Maxwell's equations. What the fuck does that even mean? And include the units at, let's go on to the next line as opposed to pushing off there, at the end of each equation. And I'm going to write here in brackets, what the fuck. And this curl of H is equal to JS no, it's not Js, it's just J plus the time derivative of D. And this one, divergence of D, is rho V. And this one is B equals 0. What? Electric, like, how? Because this is a different unit. This is a different unit. This is a different unit than this. Depending on which way you rearrange it, you can... See, I look, here's the thing. Here's the thing. There's... You're saying that the curl of the electric field is equal to B. So you're saying that B is E is somehow related to B. Right? But this has units of volts per meter squared, right? Newtons per coulomb. And this has some other units. So, what? I'm confused. I'm confused. I want to, I'm gonna write not sure about units for now. I'll come back to this next week when I've had some time to think about it, because I have no idea what the fuck that even means. That's just stupid. Sorry. I get salty sometimes when I see some strange things like this. What is this? Part C. Name every current density and include expressions in time domain. Name and define the current densities. So you have the conduction current. So the conduction current, let's call it J cond, I don't know, is equal to sigma E. Okay? And you can say this is due to charge flow. I shouldn't call it electron. I should say flow of charge. Flow of charge. You have convection current. Convection current is basically it's kind of like the same thing, but it's more of a speed thing. So, whoa, is equal to rho v times u, and so this is due to I shouldn't call that flow, I should call that charge carriers. Conduction. Should I call that conduction? Conduction. Let's call this conduction. Due to conduction in a wire. I don't know. There's very different ways you can define these. Anyhow, due to flow of charge. They're very similar. You can almost say convection current's a not necessarily in a conductor. Let's get rid of this wire thing and let's just call it a conductor, because it doesn't have to be a wire. It can be a fucking It can be an apple. You can pass current through an apple. Or a potato. Make a potato clock. Displacement. And this is JD is equal to the time derivative of t. And this is due to change in electric flux. I don't know if this is what he means by define, because a lot of these things are very unclear. And this is the source, or sometimes it's called impressed. And this does not have no equation. Due to antenna or other source of current. Somebody sent an answer for part B. Yeah, see, I don't. Okay, fine. Okay. What was written here? Let's go. Let's say volts per meter squared. Let's say amps per meter squared. And this is coulombs per meter squared. This is Webers per meter squared. Meter cubed, sorry, isn't it? Yeah, these should be cubed, I believe, because they're volumes, right? There. I don't know. I don't know what the fuck that means. Don't ask me what it means. Don't ask me to explain that to you. Don't ask me where it comes from. Don't ask me any questions about this answer, because I don't know how equations have units that relate to different fields. Sometimes I feel like he just makes things up. Like it just comes to him in a dream. Or something. I don't know. What's next? What's the next part? Part D? D. Express the time domain magnetic flux density determined is dependent on the relation to the frequency domain. Okay. So let's express time domain B show dependency on R and time in relation to frequency. Okay, B, as the function of space and time, is equal to the real component of Bs e to the j omega t. I hope that's right. I don't know if that's right. Matter of fact, I don't know if anything's right anymore. Oh, no, there's one thing I think I'm missing. This should also be dependent on space, right? I think so. BSR. There you go. That should be okay, I think. I hope. Okay. Cool. So, part E. Doesn't this feel like a scavenger hunt? Like a very hard scavenger hunt that if you don't know anything about anything or anything about electromagnetics, you basically dead in a ditch somewhere. It's certainly what it feels like to me. Free space, source free, Write simplified Maxwell's equations in time domain. Okay. Free space. Source free. What else? That's it. Write Maxwell's equations in time domain. I should say point form, right? It says point form. Point form. Point form. Derive wave equation in terms of E. What is the propagation constant? Constant? Coefficient? Constant. Okay. What are the equations in free space? Curl of E is equal to minus time derivative, right? I hope so. Mu naught dH by dt. And it's weird, I know, because nowhere in the question does it say to write things in terms of H and E, but he still wants you to, and you're supposed to know that somehow, because it's in source free and charge free or free space, whatever the fuck it is. It makes no sense to me. I lost marks on a test for this as well because I didn't, nowhere does it say to write in terms of the electric field and the magnetic field, and if you don't write everything in terms of E and H here, you lose a bunch of marks. But there's no way you can possibly know that you're supposed to do that, but you know, it is what it is. Curl of H is equal to what? This is epsilon naught. And the divergence of E is equal to 0, and the divergence of H is equal to 0. So the wave equation we can write here. How do we write the wave equation? Wave equation, we do this. Remember, I hope you guys have been practicing. You take the curl of the electric field. Well, let's not do that yet. Let's say wave equation. Let's start with this equation, because this is a nice equation to start with. Let's take the curl of both sides. Let's do this so we can be a little more appropriate. So you do this. Now you can take the curl of a bunch of stuff. This curl of the curl from a vector identity is the gradient squared of E plus the second derivative. No, it's the gradient of the divergence. Gradient of the divergence. No, gradient of the divergence of E equals minus mu naught times the time derivative of the curl of H, I hope. This divergence is 0 from this equation, because it's free space and source free, which implies charge free as well. So what you have is the gradient squared of E is equal to minus mu naught the time derivative of epsilon naught the time derivative of E And so you get that the gradient squared E is equal to minus, let's bring everything over to this side, so it's plus the second derivative of E with respect to time. Probably should have put mu naught epsilon naught in front of it, but that's okay. My mouse just disappeared, there it is. And then we can flip the sign. Minus mu naught epsilon naught divided by t squared equals 0. And we know that gamma squared has to equal mu naught epsilon naught, and that means gamma equals square root of mu naught epsilon naught. So is it that? Right? Because this is time domain, right? So there's no omega. But his answer has an omega. But that answer is wrong. That looks wrong to me. There should be no omega. This is time domain. Anyhow. And this is your... No, we're not done yet. We're not done yet. This is... Well, it's not equals, it's minus gamma squared. Gamma equals square root mu naught epsilon naught. That should be the answer. I hope. It looks like it's the answer. So, okay. More Maxwell's equations. Yay! Let's write the integral equations now. Fuck. Holy crap. Repeat. Part B. For... Is that part B? It's time domain. That's also time domain. Yep. For integral form. What are the integral forms? The integral forms are the closed line integral of E dot dl. No, wrong. Is equal to the surface integral of j dot ds and plus, no, it's not j dot ds, that's Ampere's law. What are you doing? Crazy. Does he do the arrows and stuff in his solution as well? Where are your arrows at, bro? Bro. No arrows. His answer is wrong. For part F. Oh, it's version A. It's probably a different version. Never mind. No, he's okay. Oh, he did include the arrows. Joke's on me. Okay. He did include the arrows. What the hell? Why can't I draw integral signs on this fucking fucking tablet. Good enough. L is h dot dl is equal to the surface integral. That was a nice one. J dot ds going up that way plus, does he break it up into two terms? He totally does. Plus, does he put the derivative inside or outside? I don't know. It's a tough one. This is the time derivative of d dot ds upwards. So maybe we can label them 1, 2, so you know where things start and finish. And we can probably call this one 3. And this is the closed surface integral of d dot ds is equal to the volume integral of rho v dv, and 4 is equal to, or not equal to, 4 is the closed surface integral of b dot ds is equal to 0. So you see, while this is extremely tedious and annoying to do, you can literally get 40 marks for just writing Maxwell's equations. Sounds like a pretty good deal to me, if you ask me. I don't know. It looks pretty easy. This looks like a pretty easy midterm, actually, relative to some of the other ones. Part G is repeat. No, there is no repeat. Right. Let's repeat F for the frequency domain. Repeat F for frequency. And I'm not going to do it. I'm just going to say replace time derivative with j omega and all variables, or all field quantities, or physical quantities, field related quantities have a subscript s. That was a fun question, wasn't it? He puts the derivative with respect to time outside the integral. Does he really? I don't know, because I did that once and he got angry at me. He's like, no, it should be inside the integral. Fuck you. He's like ready to like throw me out of the window. I don't know. Just do whatever he does. Put it inside or put it outside. Put little arrows around your integrals. Sure. Do what he does. I don't know which one's more correct. So here we have a TEM plane wave. Propagates in semi-infinite region, free space, x less than 0. Normal incidence on non-magnetic dielectric for x greater than 0 with epsilon r equals 4, region 2, and this is region 1. And then you're given ESI is equal to 120 pi e to the minus j pi x AY volts per meter. Okay. Yeah, I don't know what his rationale is for why he does what he does. Because like I'm saying, one time I did that, I put it outside, and he said, "No, it's not right." And I put it inside, and he said, "No, it's not right." And then I just kind of gave up on life after that. But you know, what do we have? Okay. Okay. Let's draw this thing. Hey, let's not be throwing around words like that. I can't condone that behavior, at least not while I'm doing something like this. If you want to talk to me offline, then I might have different opinions. But just for the sake of being right. So this is Z. No, this is not Z equals 0. This is X equals 0. X equals 0. This is region 1. This is region 2. And in region 2, we have mu r equals 1, epsilon r equals 4. Therefore, some stuff happens there. Epsilon r equals 1, mu r equals 1, eta naught equals 120 pi. What do we have for the waves? We have some crap like this. This, imagine, is your EI. Okay? And then you have your ET. And you have, what else? You have reflected ER. Okay. This component is in the y direction. So while it's propagating that way, its component is actually like this. So that means while this is x equals 0, this is actually y, right? So the y-axis points upward, the x-axis points this way. So if this is y and this is x, that means z comes out of the page. Z, so z out, well, let's just draw it here. Let's just say that this is y, this is x, and then this is z. Did everybody understand how I was able to decompose that? Because you should be able to do this, and you'll probably be expected to do this. Okay, so that means each wave, the way he usually likes it done is that each wave can be drawn something like this, so that E let's do this. E goes up. What should I do to get Z? What did I do to get Z? Good question. What did I do? If this is Y and this is X, then Z has to be out of the page. Because if you think about this, this is X, this is Y, then Z comes up like this. And basically, if you rotate this, so if this matches this, and this matches this, then this matches this, right? To be honest, I don't even think right-hand rule. I mean, that's what I did, but that's not how I actually did it in my head. In my head, I imagined a three-dimensional thing, and I just rotated it. So, yeah, sorry. Probably should have been more clear about that. So if I have E in Y and I'm propagating an X, that means the H that's propagating should be what? Should be the direction of propagation with the right or the direction of propagation cross the direction of the field, right? So it should be, if I'm propagating in X, I'm propagating in X, and my component is in Y, then I go X cross Y, and that means this H component, HI, should be coming out of the page. And similarly, in this case, you have the same thing. The transmitted wave will be in the same direction, and so the transmitted magnetic field will also be in the same direction, also in Z. And then you have this reverse wave, since it's going in the opposite direction, but the wave is also propagating in that, but then the component is also in Y, but it's negative the direction of propagation. It becomes Y, or it'll be negative X cross Y, which means the field H here has to go into the page. Because now what you have here is your direction of propagation is in the opposite direction, but your field component is still the same thing. So that's worth marks. So you should know how to do that. Okay. Now let's do part A. Phase constant in of the incident wave. So, in the general case, we have E is equal to E naught e to the minus j beta, let's say Z, for example, right? I don't know. Or let's compare it with the general case of what this would look like. It'll be j beta x and then ay. And so if you compare the general case with this, you see that beta is equal to pi. So beta equals pi radians per meter. And part B asks the phase and attenuation constant of the transmitted wave. Okay. Phase and attenuation constant of the transmitted wave. This, well, first of all, the attenuation constant alpha is equal to 0 because there is no loss in region 2. Okay? Okay. Now, as far as beta is concerned, because you don't have calculators here, and I don't know how you may have planned on doing this, let's do this. Let's imagine you have beta 1 is equal to omega 1 square root of mu epsilon 1. Right? Right. This is an equation that you should know from Physics 125. And by the same token, then, beta 2 is equal to omega 2 square root of mu 2 epsilon 2. And therefore, beta 2 divided by beta 1 is equal to omega 2 square root of mu 2 epsilon 2 divided by omega 1 square root of mu 1 epsilon 1. Now, if I were sitting in class with you, I would have asked you, what do we know about omega 2 and omega 1? The answer is that omega 2 is actually equal to omega 1. Let's call it omega, because the frequency of the wave doesn't change as it passes through the different mediums. What does change is the speed of the wave, and the phase of the wave might change, but the frequency of the wave itself can never change. So if the frequency of the wave can never change, or in this case, I mean, you might have some very strange cases where it might change, like in like some non-linear type of region, but this is a dielectric, so you don't have that. So if that happens, then what you can say is that these two can cancel. And you have beta 2 is equal to beta 1 times mu naught mu r2 epsilon naught epsilon r2 divided by mu naught epsilon naught, right? Because it's free space in the first region. So your mu naughts can cancel, and your epsilon naughts can cancel. And you know that this thing is 1. So you have beta 2 is going to equal beta 1 times square root of epsilon r2. And this beta 1 is pi times the square root of 4, which is 2 pi radians per meter. Now, this is a very simple question and had very little to do with electromagnetics. But unless you knew this little sneaky little trick here, technique, you wouldn't be able to solve this problem. That's why we do tutorials. See. Let's find the intrinsic impedance in the dielectric. Okay. Again, we have a little bit of a trick manipulation thing that here. So we can say eta 2 is equal to mu 2 over epsilon 2, right? That's the definition. It's mu over epsilon. But we see that this is equal to mu naught mu r, let's call this 2, divided by epsilon naught epsilon r2, all under the root. And I can split this now into mu naught over epsilon naught times mu r2 over epsilon r2. I know that this first term is equal to 120 pi. it was given in the question, and this is something I should know because I understand electromagnetic theory and I know what free space characteristics are, hopefully. And this becomes 1 over 4. And so this is 60 pi ohms. Well, technically the whole thing should be boxed, but that kind of goes against everything I stand for. So what I'm going to do is take it to the next line and say eta 2 is equal to 60 pi ohms. Okay. Part D. Where did my mouse go? Oh, there it is. Frequency domain. What? Magnetic field. Frequency domain. Magnetic field. The incident wave. Wonder if our lab kits will have 60 pi resistor values. What is 60 pi? 60 times 3.14? That's 180 roughly, isn't it? Yeah, you totally have that. Of course you have that. 180 ohms of relatively, well, it might be a little more than 180, but 180 is more or less, it's a fairly standard number. What do I want to look at now? Okay, has he showed you guys the relationship between this, where you can say, I don't even remember what the equation is. I have it here. Never mind. I lied. I should look at my notes. There's a couple of ways you can solve this. One way to solve it is to use Maxwell's equations every time. I don't know if you want to use Maxwell's equations every time, so I'm not going to suggest that you should do that. Where's the general equation? He should have mentioned it in class, because that's one of the only things he does that's useful. Okay, sure. So you have this. You have HS in a TEM. In a TEM, you have HS is equal to AP cross ES divided by eta, and you have ES is equal to n cross the other thing, or eta cross the n. Eta cross the other thing, right? I hope. So this would be eta HS cross AP, where AP is the direction of propagation. Has he discussed this in class? I'm just trying to confirm that the equation is correct. I know, yeah, it's correct. Okay. Oop, sorry. So this is true here. So that means HSI is equal to AP cross ESI divided by eta naught. And AP is the direction of propagation. If the direction of propagation in this case is x, it's in the x direction, is x. So this is AX cross ESI. The magnetic field, or so the electric field, is 120 pi. E to the minus j pi x, and this is divided by 120 pi, and this is in the AY direction. X cross Y as advertised is Z. So this is e to the minus j pi x in the AZ direction. And does he want units? I don't know. Let's give him units. I did it again. I put it all in the same line. Stop doing that. Because I don't have anything to put a box around. If I don't have anything to put a box around, then it feels like the answer is not complete. Let's put a box around this. Okay. I can live with that. What's next? E. Time. Oh, wrong color. E. Time average pointing vector in the incident wave. The incident and the time average pointing vector is the one that's the real, right? 1/2 real of the thing times the conjugate. E cross H, whatever. So PAV. Well, I don't need to put time average. Time average is. Is it a function of time? Did I write the function of time last time? I don't remember. Where is it? No. Didn't write anything there, so that's fine. 1/2 real EI cross HI conjugate, and this is 1/2 what? E cross H is going to be in the Z, we know that. This will be 120 pi e to the minus j pi x a y, right? It's a y, right? Why am I? Why? Yeah, it's a y. Why did I get confused? Cross e to the minus j, positive j pi because it's conjugate. Sorry, I just had a major brain fart there. And this should be the real component of that, but joke's on them because the whole thing's real. So this should be 1/2 times 120 times 1 y cross z. If I recall correctly, y cross z should be ax. So this should be 120 pi divided by 2. So this should be 120 pi ax. And this is, did it again. Put it on the same line. Stop putting it on the same line. Fuck. PAVE 60 pi ax. Units are watts per meter squared, I want to say, because it's a power density. Is it watts per meter? What does the textbook say? The textbook, it is watts per meter squared. Good job, dude. What else? F. What's F? Reflection coefficient at the interface. F is gamma at the interface. How do we find gamma at the interface? Good question. Good question. What do we have? Gamma at the interface. Oh, gamma is equal to eta 2 minus eta 1 divided by eta 2 plus eta 1. In one case you have 120 pi. In the other case, you have 60 pi. Oh, it's the other way. You have 60 pi minus 120 pi divided by 180 pi. So you end up with negative 60 divided by 180. I put the equal sign on the same line again, but gamma is 1/3. Minus 1/3. Okay. Gamma can be negative, yes. All that means is that the wave that's being reflected has an inverted amplitude. Gamma in general, the magnitude of gamma is the thing that you might be thinking about, because you might probably thinking about what I mentioned here. This thing. It's the magnitude of gamma has to be between 0 and 1. Gamma can be negative though, yes. What this implies is that the magnitude of gamma equals 1/3, but that there's a phase shift for gamma, which is -1, which is 90, negative 90, depending on how you define it, right? So, yeah. There's just a phase shift, that means. It's 180 degrees phase shift, not 90. What the fuck am I talking about? Gamma is 180, because it'll invert whatever wave is coming into it. Part G, the transmission coefficient. So tau at the interface. This, we have 1 plus gamma equals tau, which means that tau is equal to 2/3. Right? That's the equation, right? 1 plus gamma? So I got it wrong initially. Now I remember it's the other way. Which basically tells you you have a whole wave coming in, 1/3 of it gets reflected, and 2/3 of it goes through. There you go. Well, that's a sort of intuitive way of thinking about it. I don't know if that's the whole story. Let's find the frequency domain. Or let's just, why did I even do that? Could have made that so much simpler for myself. Anyhow, electric field intensity of the reflected wave. So remember, gamma equals ER divided by EI, which implies that EI times gamma is equal to ER. That means ER or SR, I think it calls it. That's the general sort of idea that you have to follow. So that means ESR is equal to minus 1/3 times 120 pi e to the... See, there's two ways you can take this now, right? And here's what I mean. I can either say this is positive j pi x, because intuitively I know that it's reflected, so it has to be in the opposite direction. Or the more correct way to do it is to say, or you have ESR is equal to 1/3 e to the minus j pi. Does that help? Because this thing is -1. And then that thing, that's just a longer way of doing it. Don't do that. Ignore that. It's just going to confuse you. What I was going to say is that there's a phase shift of 180, And so that phase shift to 180 makes it go in the opposite direction. But then doing this, then you have to actually do all this and manipulate the exponential, and that's just going to be messy. So just remember, the reflected wave goes in the opposite direction. So I will put a circle here and say reflected wave is in the negative x direction. Because you can always manipulate these exponentials to do whatever the hell you want, so it doesn't really matter. And what is this? 120 over 3 is minus 40 pi e to the j pi x a y volts per meter squared? Or volts per meter? It's volts per meter, isn't it? Squared? No, it's newtons per coulomb. Newton is kilogram meter per second squared. Then why the hell would this be meter squared? This should be just meters. I hope. Apparently I don't know what I'm talking about. HI. Let's do this. Let's say E S T. See, that's what I meant. I could have made it simpler for myself. You have tau is equal to E T divided by E I. And so that means E T is equal to tau E I. So E S T is equal to tau, or let's just throw it in there and say 2/3 times 120 pi e to the minus j pi x a y. And so E S T is equal to 80 pi e to the minus j pi x a y. Okay. So here I'll make the same note, but with the opposite meaning, saying transmitted wave is in the same direction. Okay, what's left? H, I, J. Okay, so J is S in region 1. So S in region 1, or S in general, is equal to 1 plus gamma divided by 1 minus gamma. So this is 1 plus 1/3 over 1 minus 1/3. 1 plus 1/3 is 4/3. 1 minus 1/3 is 2/3. Thirds cancel. 4 over 2 gives you 2. And I put it on the same fucking line again. For this next part, because this is actually something of interest, what I'm going to do is I'm going to ask you, what do you think this question, what do you think the answer to part K is? Part K. S in region 2. What is S in region 2? If it's 0, why is it 0? If it's 1, why is it 1? If it's anything else, why is it anything else? We need answers. And we need answers with reasoning. It's not enough to just, say some shit for the sake of saying some shit. What's the equation? What is the equation? Right. That's exactly it, actually. This is 0. This is 0. Why? Think about what this think about what this is. They're telling you that you have this boundary here. You have this goes to negative infinity. This goes to positive infinity. And literally there's nothing else there. You can't reflect off of anything else here. If you can't reflect off of anything here, there's never going to be a standing wave in this region. That's it. So that means the maximum and the minimum of the wave are going to be the exact same, meaning s equals 1. Because s can never equal 0, right? S is between 1 and infinity. There's no reflected waves in region 2. Exactly, that's the reason. Part L. That looks more like a weird D. Assuming region 2 becomes perfectly conducting. Okay, sure. If region 2 becomes perfectly conducting. Conducting. What are we looking for? We're looking for find S in 1. Find H S in 1, and then frequency domain surface current density is KSS at x equals 0. I don't remember what that boundary condition equation is. Fuck. Okay. Let's imagine this. What happens here? Now they're saying this is x equals 0. And all of a sudden what happened here is sigma is now infinity. That means this thing here, you will never have a field that is present in a perfect conductor. Therefore, whatever goes in, let's say this is EI, HI, will be entirely reflected. So this is ER and HR, right? So, if this is perfectly conducting, what this implies is that gamma is equal to 1, because the entire wave gets reflected entirely, right? Now, if the overall wave gets reflected entirely, then what you end up with is S is now 1 plus the magnitude of gamma, and this is 1 minus the magnitude of gamma, and so this is 1 plus 1 divided by 1 minus 1. So you have 2 over 0. And surprise, what happens now is S equals infinity. I don't know if that's a surprise to you, but when you have total reflection, you have infinite standing wave ratio. That's the case. That's S in 1. What's HS in 1? If you have, did we find the incident magnetic field? We did, didn't we? We did. HSI is, well, let's find the reflected magnetic or electric field first, and then we can find, so HSI, let's just cheat a little and copy this and say, whoa, what happened there? Oh, okay, copy and paste. Why is it pasting over there? Paste here. Okay, sorry, technical difficulties. That's the incident, but we can't use the reflection coefficient directly with the magnetic field. Remember we mentioned this earlier, so it has to be the it has to be with the electric field, right? So what I have to do then is I have to say ERI is equal to gamma times E. It's not ERI, what the fuck is that? ESRSI. That means they're equal, but they're in the opposite direction. So this is also going to be 120 pi, but this will be e to the positive j pi x ay. And if this is your reflected, then that means your HSR is going to equal eta times ESR cross AP, right? Right. This is then going to be, let's just call it eta naught for now. Let's not actually, let's just throw everything in there and see what the hell we got. This is going to be 120 pi times 120 pi e to the j pi x ay. But now this is propagating in the opposite direction, so this is positive. So this should be cross negative ax, because it's propagating in the negative ax direction. Okay. Yes. There is also such a thing as too much information. HSR will be equal to 120 pi all squared. And this will be e to the j pi x and ay cross negative, no, that's not negative, ay cross negative ax is equal to az. So that is your reflection coefficient, or your reflection, or your reflected wave. What was the question you had asking? The total frequency. Okay, so the total in the frequency. I don't know why I didn't just look at this and realize it's propagating in the opposite direction. What an idiot! So stupid. Anyhow, HS, let's call it 1, is equal to e to the minus j pi x az plus 120 pi squared e to the j pi x az amps per meter squared. That's that. Surface current density. It is... I forget the equation. We solved it, didn't we? It's like K1 minus K2. It's the boundary condition. I don't remember the boundary condition. Who remembers boundary conditions? Not I. It was like in this... Was it here? No. Was it here? Where'd you go? It was here. Surface charge, H1s minus H2s. Let's take this, steal this for a second. Bring it here. So this is the surface current density. This is like this. So, what's going on here? In region 1, we have this field. In region 2, we have 0 field. So, this is 0 indeed. What you end up with then is you have H1, or HS1, whatever the hell you want to call it, cross AN12. AN12 is AX. Is equal to KSS. Is that a vector? It is a vector. It's a cross product. And so KSS vector is equal to this whole thing, e to the minus j pi x a z plus 120 pi squared e to the j pi x az cross ax. And so KSS is equal to z cross x is ay, right? So this is e to the minus j pi x a y plus 120 pi squared e to the j pi x a y. This is current, surface current density, so it's amps per meter squared, isn't it? It's current density, I think. I hope. And that's the end of the question. That was a long frickin' question, wasn't it? Right. Well, at x equals 0, we're not done yet. We're not done yet. So, at x equals 0, but wait, there's more. Like those infomercials where they're selling you like some towel that can like clean everything. Or like some fucking tape that can like stop your boats from sinking. The boat thing looks really good. Should give it a shot one time. Just to say I did. So KSS is equal to AY plus 120 pi all squared AY, or KSS is equal to 1 plus 120 squared pi squared AY amps per meter squared. Flex tape, yes, flex tape. That's what I was talking about. The ShamWow guy died, right? I heard that he died, or I think it was somebody else. That guy was on some shit. Like he was like on some serious like speed all the time. Like I heard somewhere that he died though, or like he had like some complications or something. I don't know. But yeah, that's the end of the question. Are there any questions about this question? He got arrested? Was that it? Yeah, there's something going on with that guy. He was like he got involved with like some really heavy shit or something like that. And he just fucking I don't know. You can tell he was like on some shit though. That guy was not normal. That's the end of the question. Any questions about this question? Or about anything else in general? We can spend a few minutes talking about stuff. And I will export these notes as requested. Whoa. To documents. Shortcut this folder to your OneDrive. What is this? I didn't make this. Oh, it's all in OneDrive now. That's why. Okay. I can dig that. Okay. Bill Nye dealing drugs? He might be. No, Bill Nye doesn't deal drugs. What am I saying? Bill Nye's a cool guy. Good guy. Yeah, okay. Any questions and stuff? Anything at all? If there aren't any questions, then I'm just gonna head off. Because I'm tired as hell, and it's, I'm going to school tomorrow, so. Yeah, you too, dude. No problem. I'm glad I could help. Going to school on a Sunday, yes sir. I don't know, I've been feeling more focused at school than I have been at home lately. I've been spending a lot more time at school than I used to before, and I'm feeling very focused there, so I can't complain. And when I go through periods of very like solid focus, I like to keep the momentum going, and so I do whatever I can, even if it means going to school on a Sunday. I'm probably gonna wake up at like 4:30, 5 o'clock tomorrow. and then I'll be there by about 6ish, and then I'll probably come home early though. But yeah, I don't know. I like to. There's like different sort of rhythms and waves that you kind of get into. I feel like, at least. So for me, that's the way I usually work. So like, there was a time where I would have been really efficient and very well focused at home. Now I don't feel like that, and then so now I'm at school all the time. But then 6 months from now, I might feel better at home, so I'll start going home and doing things at home. But so I'd like to switch things up and keep things fresh and all that. But yeah, I'll be there tomorrow for a bit, mainly just reading papers and stuff. And then I've been trying to modify a power supply. So I had an old PS3 laying around that doesn't work, so I've been trying to modify that power supply to use in a Tesla coil, which I mentioned. I mentioned the Tesla coil last week, but so I want to modify that power supply and start building the Tesla coil, because Tesla coils are awesome. And then I've been looking into research topics for my PhD, and then potential afterwards, things that are of interest. And so I've got some fairly interesting things that I've come across. Some very interesting ideas that I have. So I'm hoping that after I put this Tesla coil experiment into place, which should be done in like a week or so, maybe less, I plan on building a couple of other things. So yeah, it should be interesting. So I want to spend as much time as possible as doing that kind of stuff, just to progress more in that regard, because I feel like I've done a lot of theoretical stuff, but I need to do more practical. What am I going to do with the Tesla coil? I'm going to do absolutely nothing to it. I'm just going to make it, let it shoot some sparks around, maybe zap myself a little bit here and there, and then just put it in the back of the lab somewhere, because hey. So yeah, but after that I have a couple of very interesting ideas about things that I want to try, so they should be fun, because I'm hoping to tie those ideas into the PhD work that I'm doing. And I'll comment more on that when I actually have something that's concrete, because I don't really have anything solid right now. I'm just kind of have a couple of ideas that I'm thinking about. They're not even very coherent ideas. They're kind of just, random shit. So yeah. I don't know if that would be successful. I think there's an immunity that's been developed there in regards to that kind of a stimulus, um based on the person's history, based on, so I think it'll probably backfire on me, and it'll hurt me more than it hurts him. I've been thinking of, I don't know if this is a good idea, if anybody wants, or anybody would be interested, or anybody would participate, but I've been thinking of, because I spend quite a bit of time working on, I showed you guys the book that I'm working on with the figures from MIT. I I've been thinking about maybe streaming that, and not necessarily streaming it for the sake of streaming the figures, or oh, I'm doing something so cool, just for the sake of streaming to hang out, and chill, talk about stuff. I don't know if anybody would be interested in maybe once a week or so. Yeah, I don't know. I might do that. Maybe next time. Next time is going to be what? Probably tomorrow evening. So, second monitor is so good. Oh my god. I got it last week. Didn't set it up. I set it up right after the tutorial last week. And it's so good. But I didn't get to set it up properly until today because before I had just, they were sitting on my desk. My desk didn't have enough space, so I had to move some things around and this and that. I had to like rebuild the hutch I have on top of it as well. But today I ordered like a dual VESA mount from Amazon, and so I set that up today, and so now there's no stands on the desk. I've spaced out the hutch itself. I've managed all the wires really well, and 144 hertz. Is it 144 hertz? I know one of them is. The other one, I don't know. I can't remember what the other one is. And so yeah, I've set everything up properly, and so it's really exciting because now it's like, it's just so nice. Like I have such a good time just looking at my screens now. So yeah, that's exciting. But other than that, but now I have a whole mess to clean up in the basement, so I'll probably do that tomorrow as well sometime. Anyhow, I think I'm gonna head off because it's late. I have to get up early, so I might do something tomorrow. If I do something tomorrow, then I'll probably post it here in this group or something like that. I don't know if I want to use Facebook to stream that though, because Facebook seems to limit the quality at which I can stream. I can't stream beyond 780 for some reason here, or 720. So I might use Twitch because I know that Twitch has let me stream 1080 before, but I don't know. I can't be sure. Anyhow, yeah. You guys have a great weekend as well. For anybody who's celebrating, happy Thanksgiving. For anybody who's not celebrating, have a good long weekend. And yeah, we'll see you guys next time. Whenever next time may be. Should be next week, I hope. So yeah. Alright. Later, guys.